Hi folks, we're going to continue where we left off in lesson 3, and just a reminder of where we were at. We saw that if we were taking a limit of a quotient, say f of x over g of x, and both numerator and denominator approach 0, we saw that in some circumstances the limit existed, and in other circumstances it didn't. We also saw that when the numerator and denominator both approach infinity, we had a similar scenario. Sometimes the limit existed, sometimes it didn't. Think and behavior rational functions. So in these circumstances where the form produces the possibility of a limit existing or not existing, where we don't know, it's not determined until we do some more investigation, this is what we called the indeterminate forms. Okay, and these are the two that we're going to deal with most often in this course, but there's actually other indeterminate forms. Another one is infinity minus infinity. So what if both functions that we're subtracting are approaching positive infinity? You might sort of think, oh, maybe they'll just cancel each other out. But if you think of the example 2 to the x minus x squared, and we try to determine the end behavior as x approaches positive infinity, you have a big number being subtracted by another big number, but the first one is significantly larger. All right, so the end result is that this is still going to approach uh, positive infinity. Is that going to be the case in all circumstances? So that's one thing you're going to take a look at. And another indeterminate form is 0 to the 0. So this one's a little odd because when you think of a power where the base is equal to 0, well, you expect the power to just be equal to 0. Whereas when you have a power with an exponent of 0, you expect the result to be equal to 1. So which is it, if either? All right. So these are what you're going to explore. So in a second, we're going to pause the video and you're going to work on these three limits. Okay, for this one here, you notice it's an infinity minus infinity scenario because they're both getting large and approaching infinity. And these here, they both approach 0 to the 0. All right, just a reminder of the trick we often use when dealing with variables inside of the square root. So now I'll ask you to please pause the video for about 7-8 minutes to give everybody a chance to work on these. All right, so we're back, and let's take a look at this one here. So the indeterminate form that we're dealing with is infinity minus infinity. Okay, so we're going to want to sort of do some algebra here, but of course we've got this x squared that's stuck inside the square root. We can't operate with it with the x outside the square root, and so hopefully you thought of using that trick that we use very often with square roots, the idea of multiplying by the conjugate. Okay, so I'm going to multiply this expression by square root of x squared plus 1 plus x. But of course, I can't do that. I've changed the expression, so I'm also going to divide by square root of x squared plus 1 plus x. So essentially, I've multiplied it by 1. Okay, so in the numerator, we have our difference of squares. Okay, so these two square roots multiplied to each other is just going to give us x squared plus 1, and then minus the product of these two expressions, minus x squared, all over square root of x squared plus 1 plus x. And here we see that something very nice happens. Those x's in the numerator cancel each other out. And what I'm going to be left with is something that I can determine. Okay, because here we have the numerator is just equal to 1, and the denominator is just two very large numbers being added to each other, getting larger and larger and larger. So here we can infer that the limit of this expression is just going to be approaching 0. And so we see that the limit does exist. It's approaching 0, okay? Different from when we had 2 to the x minus x squared, where both expressions were approaching 0. So this confirms that infinity minus infinity is another um, indeterminate form. Okay, so here now we're going to investigate this limit here. All right, so what we've got we've got the limit of x to the 0 as x is approaching 0 from the right. But we notice here that when I've got numbers not equal to 0 in the base, these values are always going to be equal to 1. So, 0.1 to the 0 is 1. 0.01 to the exponent of 0 is 1. 0.0001 to the exponent of 0 is equal to 1. So any base that's not equal to 0 to the power of 0, we know has to be equal to 1. All right? Similarly, in this limit, what we see is that when I'm taking values, remember, I'm not dealing with the number 0 itself, I'm just approaching 0 from the positive side. So when I have 0 to the 0.1, 0 to the 0.01, 0 to the 0.0001, all of these expressions are just going to be equal to 0. And what this does is it confirms that 0 to the 0 is an indeterminate form. Okay? Different limits can lead to different results. So 0 to the 0 technically is an undefined expression. Now, having said that, there are times when it's useful to define this as being equal to 1, but technically the expression is undefined. And when we see it in a limit, it's an indeterminate form. So here we had to investigate, we had to actually figure out what these limits approached, and we saw that they actually approached different numbers. Okay? But as I said, these are the two indeterminate forms that we're going to be focusing on. All right? So now I want you to use this idea, all right, of the fact that if I've got a quotient and the denominator is approaching 0, the only way for the limit to exist is if the numerator is also approaching 0. Because remember what we found. If it was only the denominator approaching 0, the limit did not exist. So I want you to try to use that idea to solve this problem here. Okay, so at this point we're going to pause the video and give about 5 minutes to work on this problem. All right, so we're back here. So I'm actually going to take two approaches to this question here. I'm going to take a more intuitive approach. I'll call that approach 1. And then I'm going to take a more formal approach, a more algebraic one. Okay, so let's see what this is saying. It's saying that the limit of as x approaches 3 of this quotient is equal to 7, but the limit of the denominator is equal to 0, and they want us to determine the limit of the numerator function as x approaches 3. Okay, now this is where we have to be careful, because the fact that this limit is equal to 7 tells us that the limit exists, but the denominator is approaching 0. In many cases, the denominator approaching 0 means that the limit doesn't exist unless something else happens, unless the numerator is also approaching 0. And that is the reasoning we're going to use here. Is we're going to say, since this limit, the fact that it's equal to 7 is of really no consequence. The only thing that matters is that the limit exists. Okay? And we know that the limit of the denominator is equal to 0. Okay? The only thing that can happen, okay? The only thing that can happen is that the limit as x approaches 3 of f at x must also be equal to 0. Okay? Otherwise, the limit could not exist. Okay? And so this is our reasoning, is the limit of the quotient exists, but the denominator is approaching 0. And as we saw earlier, the only way for the limit of a quotient where the denominator is approaching 0 to exist is if the numerator also approaches 0. If the numerator didn't approach 0, it could not exist. Okay, and this is again very intuitive argument based on that idea. Okay, but I would like to show you, when we can do something a little more uh, algebraically, I think it is good to see it. Okay, so this is what I'm going to call my more formal approach. Okay, so what I'm trying to find is I'm trying to find the limit as x approaches 3 of f at x. Okay, but the information that I'm given is about the quotient f at x over g of x. Okay, sorry for the stutter there. This is the information that I'm given. So what I want to try to do is I want to try to use the fact that I'm given the limit of f at x over g of x. Okay, so somehow I need to get an f of x over g of x. But look at what I just did. I just divided by something that wasn't there before. Okay, so what is the only way I can get away with this is if I also multiply by g of x. And I see that this is equal to the limit of f at x as x approaches 3. Okay, so again, it's similar to the trick we use above. If I divide my expression by some other expression, but I also multiply it by that expression, okay, I can now, do that legally. I haven't actually changed the value here. Okay, but now look at what I have. I have the limit of a product. Okay, and remember those limit properties. The limit properties say that I can break this up as the product of the individual limits. Okay, but why am I allowed to do that? Remember what the condition was to be able to do that was if each individual limit existed. And that is the case. I'm told that the limit of f at x over g of x exists because it's equal to 7. I'm told that the limit of g of x exists because it's equal to 0. Okay, so I can do that because both limits exist. But now I know what the limit of f of x over g of x is. It's 7. I know what the limit of g of x as x approaches 3 is. It's 0. And of course, 7 times 0 is just 0. Okay? So this is the way I would probably expect you to do the question like this in the homework. But if you can think of a way to deal with it algebraically, it's kind of not bad to get used to that sort of thinking. Okay? So now we're going to move on to lesson